Okay, so let's go ahead and get started. Okay, so first of all, I have an announcement. If you remember from last time, I wasn't quite sure what I was gonna do if there's a strike next week, but what I've decided is that I'm gonna be here. And then depending on how many of you show up, will determine whether I lecture or not. You know, if I have, say half a class or more, I'll do the lecture. Now, there's no penalty for not attending. If you don't want to attend and, support the strike, that's your choice and that's fine. Remember, I do record my lectures, so if you don't attend, you'll be able to see the lecture at a later time, okay? Now, if, less than half the people show up, I'm just gonna have an open lab and you can work on assignments, okay? So, that's what I decided to do. I thought about it and it's just that, you all pay a ridiculous amount of tuition. And one of the things I disagree with the union is that I think they should be fighting for that. If there is a week strike, that you get reimbursed your tuition. That should be one of their demands, in my opinion. So anyway, that's what I decided to do. Okay, so again, if you decide not to come, you're not going to be penalized in any way. Okay. Okay, so today's class is on Karnaugh maps. Karnaugh maps is a way that you can reduce Boolean equations in kind of a fun manner. Okay, at least some people think it's fun. Previous students have told me that they kind of like Karnaugh maps, even though they look kind of strange at first, because kind of like a crossword puzzle. Remember last class, I gave you this handout that had, truth tables and symbols of the basic eights, but it also had all the different theorems and axioms of Boolean algebra, which again is just base 2 algebra. And, you could use these axioms and these theorems to reduce a Boolean equation in a similar manner that you do a base 10 equation by factoring and, things like that. Okay. But Karnaugh maps is a pictorial way of doing the same thing as using these laws and axioms. And like I said, it's sort of at least some people think, a fun way to reduce Boolean equations. Again, once you get used to it, because they do look kind of strange at first, okay? Now, when you're out in industry and you got to reduce Boolean equations, you're not going to use a Karnaugh map, you're not going to use these axioms, you're likely to use an algorithm. But like anything else, it's good to know another way or multiple ways to do the same thing. If for nothing else, you can check your algorithm with a technique like the Karnaugh maps. Okay, so as you can see on the agenda here, there's several things that I want to go over before we actually get to some examples. Once we cover what the basics of Karnaugh maps are, I've got, as you can see, about probably, I don't know, almost a dozen, maybe 8 or 9 examples. And then the activity for today's class are more examples. So you're going to get plenty of practice with Karnaugh maps by the end of this class. And Karnaugh maps are also involved with lab 1, your second lab, which is going to be due next week. Okay, so you're going to get a lot of practice with Karnaugh maps. So the first thing I want to talk about is when you look at a Karnaugh map like this. Now, there's 2 types of Karnaugh map that we're going to go over in class here. There's an 8 cell. Okay, each of these squares is referred to as a cell. And there's a 16 cell. And, the first thing when someone looks at a Karnaugh map that kind of stands out is that the numbering doesn't go in order, okay? You look at this top row, goes 0, 1, 3, 2, and then this next row, 4, 5, 7, 6. So, why isn't it 0, 1, 2, 3, 4, 5, 6, 7? Why is it out of order? Same thing, the same type of thing with the 16 cell. You can see here, first row is just like the first row of the 8 cell, also the second row of the 16 cell and 8 cell, 8 cell are the same. And then look, instead of having 8, 9, 11, 10 after the 4, 5, 7, 6, it skips to 12, 13, 15, 14, right? And then it goes to 8, 9, 11, 10. So, when someone first looks at a kernel map, it looks strange for that reason, because the cells are numbered out of order. Well, the cells are numbered this way for a good reason, because with the cells numbered as you see, there's a property of what's called unit distance. And unit distance just means that if you look at any, or if you take any cell and you compare it to a cell below it, or to each side of it, or if you're looking at this cell, the cell above it, and the cell to each side of it, there's only a 1-bit difference in those numbers of the cells, which are called indexes. So for example, if we were to look at cell 3 here, okay, so we're looking at cell 3. And in our truth table, here's our binary for 3. Well, if you compare 3 to 1, right, you compare these two, you can see there's only a 1-bit difference. See, the most significant bits are the same, the least significant bits are the same, but only the middle bit is different. Okay. If you compare 3 to 2, so you compare these two, again, you can see there's a 1-bit difference. Okay, and if you compare 3 to 7, 3 to 7, again, there's only a 1-bit difference. And if you were to take any cell in either the 8 cell or 16 cell and look, again, take any cell, look above, below, side to side, you would see there's only a 1-bit difference with this numbering scheme. If we had numbered this 0, 1, 2, 3, right? If we had a 1 and a 2 here, well, look, 1 and 2, there's a 2-bit difference, right? Because there's a bit difference here and a bit difference there. So that would not be unit distance. And you have to have that property of unit distance in order for this technique to work, right? So, this technique I'm about to show you only works when there's unit distance between the cells, up and down and side to side. Okay, so do you have any question about what's meant by unit distance? Do you see how with this numbering, there's just a 1-bit difference? And again, you can take any of those cells and you'll see that property.
Is that the only reason that it's like that?
Right, yeah. That's the reason for the out of order, is to get that unit distance, exactly, yeah. Okay, so everybody good with unit distance? All right, the other thing that kind of stands out when someone first looks at a kernel map is, why is there an A here? What does this line with a B mean? What does this line with a C mean? And with the 16 cell, why is there an A for these 2 rows? A B for these 2 rows, a C for these 2, a D for those 2 columns. Okay, well, the reason why is, if we look at this row here, this 8 cell that has an A, well, look at the indexes that are in that row, 4, 5, 7, 6. And now look at the truth table for 4, 5, 6, 7, right? These 4 right here. A is equal to 1 for all those indexes. So you see, that's why there's an A there, because for each of those binary numbers, A is equal to a 1. Likewise, for 0, 1, 3, 2, right? 0, 1, 2, 3, A is 0, so you could write not A for that row, right? Because remember last time we talked about how if it's just a variable, it corresponds to a 1, but if it's a 0, it's a not the variable, because not means the opposite of in Boolean, right? Okay. Okay, let's look here where there's B for these 2 columns. In these 2 columns, we have 2, 3, 6, 7. So look at those binary here, 2, 3, 6, 7. The B is equal to 1 for those binary numbers. Okay, likewise, these 2 columns would be not B, right? Because you look at 0, 1, 4, 5, 0, 1, 4, 5, the B is equal to 0 for those binary numbers. Okay, C, these 2 columns here that have 1, 3, 5, 7. Well, that's the least significant bit. So if you look at C, when you have an odd number, well, C being the least significant bit, which as we talked about is equal to a 1, if it's a binary number, well, you see that for all those four indexes, C is one. So therefore, this column and this column would be not C. Right, because for 0, 4, 2, 6, the even number, the least significant bit would be 0. Okay, and the same applies to a 16 cell, it's the same idea. See, A here for these two rows, because from 8 to 15, A is 1. Right, so these two rows would be not A. Here, these indexes, these binary numbers have B equal to 1. So our not B row would be here and here. These two columns, C is 1 for those indexes, so these two columns, it would be not C. And then here, this is your least significant bit when you have 4 variables, right, D? So those are your odd indexes, or excuse me, actually, what did I do here? Let's see, did I break that down? Did I make a mistake here? Oh, no, that's right, because again, D is the least significant, so yeah, for the odd, that would be 1. So the even, or excuse me, the even where we have D equal to 0, that would be over here and over. Okay, for some reason, I was losing my mind there for a minute. Okay, so do you have any questions about how I'm getting these variables for the various rows and columns? Everybody's good? Question?
Will it be the same, like the A will always be, like the bottom row, the B will always be the right two columns for every single, like 3 variable.
Right, right. If you have an 8 cell, you know, the 4, 5, 6, 7, that's always gonna be the A row, again, because A equals 1 for those binary numbers.
The A will never be in a different spot, it'll always be like that.
Yeah, as long, well, as long as the K-map is drawn like this, like sometimes you can have a K-map that might be oriented different, but no matter how it's oriented, the A would go with a 4, 5, 7, 6 row. Yeah. Okay. Let's see, what else here? Oh, now, to fill out a K-map, you know, what goes inside the cells are just the output for those, input, binary, those indexes. So let's say, you know, our output for this, truth table, let's say, you know, we had a 1 here, 0, 0, 1, 0, 1, 1, 1. Well, inside cell 0 would go this output 1. Okay, inside cell 1 would go 0, inside cell 2 would go 0, inside cell 3 would go 1, inside cell 4 would go 0, cell 5 would go 1, in cell 6 would go a 1, and inside cell 7 would go 1. So the outputs to the corresponding index goes inside the cell. It's the same thing if you have a 16 cell K. 1, 0, 0, so on. You would just put the output within the cell. You know, you would just keep on going. Okay. So, any questions up to this point? Okay, so everyone understands unit distance, everyone understands how I'm getting those variables for the rows and the columns? Okay, so now let's talk about the goal of Carnot math. Well, the goal is to get the least number largest grouping. Okay, what you're gonna see is that the number of groupings is gonna give us the number of terms in our reduced Boolean expression. And the larger the grouping is, the less variables a term would have. Okay, so if you get the least number of largest groupings, you're gonna end up with the shortest, the smallest Boolean equation. Now, the groupings have to either be rectangular or square. Okay, you can't have like diagonal groupings, you can't have like irregular shape groupings, they either have to be square or rectangular. Also, the groups have to be in whole number powers of 2. So you can have a group of 1, you have a group of 2, a group of 4, a group of 8, a group of 16. You can't have a group of 3, a group of 6, or any other number other than these numbers here. Okay. Now, the number of variables that each group will give you is the following based on how many number of cells you have. If you have an 8 cell and you just have a 1 grouping, now you can either group 1s or 0s, okay? And we're going to do examples of both and explain why you might want to do one or the other. But if you have just 1 grouping, that's going to give you a 3 variable term if it's an 8 cell. If it's a 16 cell, it's going to give you a 4 variable term. Okay. If you have a grouping of 2 and it's an 8 cell, you're going to have a 2 variable term. 16 cell will give you a 3 variable term. If you have a group of 4 in an 8 cell, that's going to give you just a term with 1 variable. In a 16 cell, it's a 2 variable term. Now, if you have an 8 cell and all 8 cells have the same value, whether a 1 or 0, well, that means your output equals 1 or 0, right? Because that would tell you that the whole truth table has the same output. So if you have a grouping of 8 and it's an 8 cell, that means that it just equals 0 or equals 1, depending on what you're grouping. And then if you have a 16 cell and it's an 8 grouping, you'll get a 1 variable term. Now, 16 grouping in an 8 cell doesn't make any sense, right? So that's an NA. But then in the 16 cell, if all your outputs are the same value, well, again, it's either going to be just equal to a 0 or equal to a 1, depending on what you're grouping. Okay? And in the examples that we do, you're going to see examples of this here, examples of the groupings and what terms we get from the various size groupings. Okay? But any questions to this point before we, because the next thing is to actually apply this now and do some examples. Everybody's good? All right, so let's do our first example, this one right here. And I didn't just randomly choose these examples. I chose each example for a reason because they bring, some particular concept up. All right, so let's look at this first one. And in this first one, we're going to group 1s. So remember, the goal is to get the least number of largest groupings. So anytime you're doing a Karnaugh math problem, you always start with, well, this is an 8 cell. Do I have 8 of anything, right? Do I have, in this case, since I'm circling 1s, do I have 8 1s? Well, clearly I don't. Then you move on and you go, okay, well, do I have a group of 4 1s anywhere? Well, there's only 3 1s, so they can't be a group of 4 1s. And now you go, okay, well, do I have a group of 2 1s that I could group either in a rectangle or a square? So what would you say to that? Do we have a grouping of 2? Yeah, where is it? What cell numbers? Yeah, there's 0 and 4 right here. See, I could do a grouping right like this. Okay? Now, the term that you get from that grouping, and since it's an 8 cell with a two grouping, we should get a 2 variable term. Well, to get that term, you look at what is common to that grouping. What variables is common to that grouping? So you see, here's our grouping. Both 1s of that grouping is in the not B column and also the not C column. So you see, from this grouping, we would get the term not B, not C. See, what changes in this grouping is A, right? Because this one of the grouping is in the A row, this one of the grouping is in the not A row. So the one that changes, the variable that changes, that's the one that drops out. Okay? All right, so the only thing left here is we would have a single grouping here, right? Because we can't group this one, there's no other one to group it with. So that would give us a 3 variable, and it's just going to give us the variable that, or excuse me, the term that goes with the index 3. So, you know, we would just get, let's see, it'd be not A, B, C. And you can see it's in the not A row, the B, C, columns. So since we're grouping ones, and think back to last class when we had a truth table and we looked at the ones and we wrote the SOP equation. What was that equation for? Like if our output was labeled F, was it for F or not F if you're looking at ones? Is it not F? F, yeah, you had a 50-50 shot, right? Yeah, remember, it's the zeros give you the not F equation, right? Not F SOP. The ones give you the F. So our reduced expression here would just be F equals not B, not C, or not A, B, C. Okay, so does anyone have any question on how we got this? Right, the not B, not C came from this two grouping. The not A, B, C came from this just single grouping.
Are we only looking for like groups of ones? Are we looking for groups of zeros?
Yes, you can do both. Yeah, and we're gonna do some, as I get further down, we'll do some zeros and we'll talk about why you might want to do that. Yeah, but yeah, a kernel map, you can either group the ones and get the reduced SOP for F. And then if you were to group the zeros, you get the reduced expression for no, the other one, yeah. Okay.
Could you also explain again, why the first one only has B?
Okay, sure. Yeah, because when you have a two grouping in an 8 cell, it's gonna give you a two variable term because you'll see that there's two variables that are common to that grouping. See, this grouping is in the not B column, right? Because not B are these two columns. So see, they're both in the not B, and also they're both in the not C column. See, what changes is A, right? Because this one of the grouping is in the A row, and this one of the grouping is in the not A row. So the variable that changes within the grouping, that's the one that falls out. Okay, you just keep the variables that are common to the group. Okay. Any other questions on this one? Okay, let's do the next one. Again, this next one, we're gonna group ones. And the reason I chose this example is because when you have a Carnot map, an 8 cell like this, these edges touch. So it's just like, you know, the map is like a cylinder and you kind of split it and flatten it out. Okay, so these touch. So you can group through those edges. Okay, so knowing that these edges touch, how would you group the ones here? You get, yeah, you can group 4. You can group the 0 and 4 here with the 2 and the 6, right? You see, you have a 4 grouping. Okay, and a 4 grouping is going to give you, when it's an 8 cell, a 4 grouping is going to just give you a one variable term. So you look at what's common. So what's common to these two columns here? Not C, right? Because these two columns are C, so these two columns are not C. So this would just be F equals not C. Okay. All right. Ready for the next one? Okay, again, let's group one. So what would you do first here? Again, you're always looking for largest groups, right? You should always start grouping the largest groups you can.
Square in the middle.
Yeah, the square in the middle, right? Right here, that's a grouping of 4. Okay, and what term are we going to get from that grouping of 4? Right, it's going to be C because C is what's common to that square that you just said, right? So we're going to get C. So it's going to be one of the terms we have. Okay, so the reason I chose this example is because with Carnot maps, you can overlap groupings. So knowing that you can overlap groupings, how would you take care of this one over here, right? Because we got to group this one that we haven't grouped yet.
Like the bottom 3.
Okay, can you do 3? Yeah, it's gonna be either groups of 1, 2, 4, 8, or 16. It's gonna be a whole number power of 2 grouping. So you can't do 3, but what could you do? Yeah, yeah, exactly, right? You could do 6 and 7 right here. Right, because if I just did a single grouping, that's gonna give me a 3-variable term. But by making a 2 grouping, I'm gonna get a 2-variable term, right? 2-variable term is more reduced than a 3-variable term. Okay, so what 2 variables are we gonna get? What's, 2 variables are common to this 2 grouping? A and B, exactly. They're both in the A row, they're both in the B column. Are you having fun yet? Is it getting fun now? Okay, so any question on that one? All right, so let's go crazy now. Let's do zeros. Okay, now, why do you suppose that you may want to group zeros? Like what would be a reason to get an SOP for not F? Like when we were doing truth tables last week, what was the reason that we would get an expression that was SOP for not F? Right, you can get POS4. If it's SOP for not F, when you do De Morgan's twice, it's gonna be POS4. Yeah, right, remember, because everything inverts. Okay, very good. So, see, the only difference here when you're using Carnot maps is now you're getting the most reduced expression for POS, right? Because you're going to start with the most reduced expression for not F, where when you're taking it from a truth table, generally speaking, that's not going to be a reduced expression. Okay. All right, so we want to group zeros. So what would you group first? Any ideas?
5 and 7.
You want to do 5 and 7? Now, someone's gonna help Colin out. It's Colin, right? Yeah, someone's gotta help Colin out. Colin's doing all the work here. All right, 5 and 7. What term is that gonna give us? Okay, A and C. All right, so what other groups do we have? Someone else other than Colin? Okay, 0 and 1. Okay, what term are we gonna get from that 2 grouping? Say again? Yep, not A, not B, everybody agree? Right, that 2 grouping, they're both in the not A row and they're both in the not B column, so that would give a. Yeah, not A, not B. All right, then we got this 2 over here, so how would you handle that? Right, 2 and 0, because again, these edges touch, right, so you can group through the edges. 0, 2. Actually, fit the right here. This is going to be. Sorry. Actually, let's get rid of it. Just write the term next to it here. So what term are we going to get from the 0 and 2 grouping? A. Not A, not C. Yeah, everybody agree? Not A. Now, one of the reasons I chose this particular K-map is, does anyone see that there's another solution, another most reduced solution? Because how else could you group this? 1 and 5. Yeah, we could have kept, let's see, we could have kept 0 and 1 the same, right? And 0 and 2, well, let's see. What could we check this in here? We could have done, let's see, 0 and 2. We did 0 and 2, that would be these 2. And then 5 and 7. But then did 1 and 5 instead, right? So we'd have 2 of the same terms, right? We'd still have the not A, not C, right? Because that was from the 0 and the 2. And that's the 5 and the 7. That was AC, right? But now if we group the 1 and the 5, what term is that going to give us? Well, it's going to be 2 variable. So what else? C and not B, right? They're both in the not B. Not B. So I chose this example just to show that sometimes a K-map will give you more than one reduced expression. Like you can have cases where, K-map gives you more than one correct solution, like equally reduced. Okay? Now, I made a mistake here. What should I have over here instead of F? Not F, because we're circling zero. Okay, and then as we said before, we could then go to POS for F by just inverting. And what else do you do when you go from SOP to POS? You invert all the variables, and then what else? Yeah, and the ors to ands, right? And again, you saw the derivation of that last time. Showed the two steps of De Morgan. All right, so any questions up to this point? I'm gonna turn the camera before I forget. Any questions up to this point? Because now we're gonna get to something you haven't seen before. We're gonna get to this dash here that you haven't seen yet in this class. But before I get to that, everybody's good? Okay, so let's move on to this example. And you can see in this example, there's a couple of cells that have dashes. And what the dash stands for in this case is I don't care. Or you can even say doesn't matter. Irrelevant, any of those things. And what we mean by a don't care in the digital world is that output could be a 0 or a 1. Like we don't care what it is. The most common example of a don't care, and you'll have this case in at least one of the designs this quarter, is that you could have a module, in your logic circuit, you could have a module where there's an output that is not connected. It's not that every output has to be connected. You can have an output that you're just not using. Maybe your device has, multiple outputs and there's just one or two that you're not using. And if you're not using it, you don't care whether it's a 0 or 1. Okay. Now, when you're doing a K-map, don't cares are sort of like wildcards or, like wild bits. You can make a don't care equal to whatever you want. You can make it equal to a 0 or you can make it equal to a 1. Because we're reducing equations, we want to make it equal to whatever is going to lead to the most reduced equation, which again is getting the least number of largest grouping. Okay. So let's say we're doing this example here, and let's say that we're going to group ones. Okay, so I have this K-map and I'm grouping ones. So if I'm grouping one, what would I want these don't cares to equal? Okay, which one a 1, which one a 0? Okay, you want this to be what? A 1. A 1, okay. You want this to be it? Okay. How many people agree with Colin? How many people think it should be something different? How many people don't like raising their hand? Yep, why'd you raise your hand then? I always catch somebody. This is right. This is right because see, by making that a 1, I now have a 4 grouping. See, if that was a 0, how would I have to group these 3 ones? 2 groups of 2, which is going to give me 2 terms where each term, right? If it's a group of 2 and it's an 8 cell, it's going to give me 2 terms where each term is 2 variables. By making this a 1, now I only have 1 term, that's 1 variable. So what's more reduced? 1 term, 1 variable, or 2 terms of 2 variables? Clearly it's the 1 term of 1 variable, all right? So see, that's why you always got to keep in mind what the goal is, okay? And what value is that 4 grouping going to give us? Not B, correct? Right, so see, both, or that whole 4 grouping is in the not B column. Right, and everybody can see what that would have to be a zero, right? Because if you made that a one, that's gonna give you a whole nother term, right? That'd give you another two variable term. Okay, so any questions on anything thus far?
So essentially with the dashes, you wanna make it, you wanna make them zeros or one to have like the least amount of movement.
Yeah, exactly. Yeah, when you have don't cares, it actually gives you some power, so to speak, right? Because you can make that output equal to whatever you want that leads to the most reduced expression. Yeah. Okay, let's see, this next one. This next one, we want to group zeros. Okay, so this one here, we want to group zeros. So if I want to group zeros, what would you make those don't cares equal to? Will you make them equal to all one? How many people agree with that? All ones for the don't care. Okay, not everybody. Is there some people that think we should make it zero? Any of them zero? Is there anyone that doesn't know? Okay, well, to prove that it's gonna be all ones, just think about what it would be if we made all zeros, because if we make it all ones, how many groupings are we gonna? Just one, right? This single two group. If I make any of these don't cares zeros, I'm gonna add terms. Right, which is gonna lead to a larger expression. Okay, so yeah, we just, I chose this example on purpose because, for whatever reason, sometimes people think, oh, I gotta make the don't care what I'm trying to circle. But there's cases where you want the don't care to be the other value than what you're circling, right? It's whatever leads to the least number of groups, least largest number of groups. Okay, so we would just group these two together. So we're gonna get not F. And what term are we gonna get? C not A. Now, actually, I'm glad you said it that way. I'm glad you said C not A instead of not AC, because that reminds me to tell everybody, please, when you're doing problems like this, even though not A, C and C not A is the same logically, put them in alphabetical order. Okay, it's just easier for a grader if you do that. I appreciate it. If you do. So yeah, you're right. It's not A, C. Okay, so that's the last 8-cell example I have. We're gonna do 16-cell. Now, the good news is that if you understand 8-cell, 16-cell is the same idea. The only thing that's different is, well, if you have a 1 grouping, it's a 4 variable term, 2 grouping, 3 variable, 4 grouping, 2 variable, 8 grouping, 1 variable. I mean, that's the only difference, but the concept's the same. Oh, one other difference, or one other thing that comes up with a 16-cell is not only are the edges, like the sides, connected, but also the top and the bottom are connected. So just like in an 8-cell, that you can go through the edges, in a 16-cell, you can also go through the edges on the side and also the edges on the top and the bottom. So, we were talking over here with an 8-cell, it's sort of like a cylinder, and you can split it and flatten it out. The 16-cell, it's like a sphere, and you can split it and flatten it out. So it's kind of like a, you know how you have like the globe of the earth, and then you have like flat maps of the earth. It's that kind of idea. Okay. All right, so let's look at our first 16-cell, this one here, and we're going to group ones. So this one right here, we want to group 1. So what would you do first? Again, always start with grouping the largest that you can. Yeah, exactly, right? Because again, the edges touch, so I can do this 4 group. Right, the 4, 12, 6, and 14. So a 4 grouping with a 16-cell is going to give me a 2 variable term. So there's 2 variables that are common to this 4 grouping. What are they? Yep, B is common, right? Because the 4 grouping, it's all in the B rows, and not D, right? You see the 4 grouping, it's all in the not D. So one term for this is gonna be B, not D. Everybody agree with that? Okay, what would you do next? There's no more four groupings, but what do we have? Remember, you can overlap, just like in an 8 cell.
4 and 5.
Yep, 4 and 5. You can make that a 2 grouping. And a 2 grouping in a 16 cell is gonna give us a 3 variable. So there's 3 variables that are common to this 2 grouping. What are they? Okay, say that slow now. Let's see, did you say not D? Well, this 2 grouping here, if you look at, see, D is these 2 columns and not D is this column. So, oh, you said B, I'm sorry. Okay, so you're saying not B or B? Okay, B, I agree, right? Everybody agree B, and then what are you saying for the A? Okay, not A, B. Not, C. Okay, I'm sorry, I think I just misheard you, so I'm sorry for that. Yeah, so it's not A, B, and then what do you say, not C? Okay, everybody agree with that? Right, because it's D that changes, right? Because this one is in the not D and this one is in the D. All right, well, we got this one right here. What do we do with that? Yeah, we can't group it with anything, right? There's nothing to the side, there's nothing below, right? Again, this touches, but 11 here is a 0, so we can't group that. So yeah, this is just a single grouping. I mean, sometimes you're just stuck with a single grouping, you know, you can't do anything about it. So what is that? What term is that going to be? Yeah, exactly. Not A, not B, C, D. Okay, so are you getting the hang of it? I mean. Yeah, like I said, I think this is a funner approach than, you know, more of a brute force using these laws and identities, you know. Okay, so let's move on to this one. This one also is grouping ones. Yeah, in fact, the next 2 are grouping ones, then we're going to group zeros over there. Okay, so how would you group these ones?
Well, 12, 13, 14, 15.
Yep, you got this row. What term is that row going to give us? What's common to this? AB, yep. AB. Okay, what would you do next? Now, remember, you can overlap. Yeah, exactly, yeah. If you do 5, 7, how many variables are you gonna get? 3. If you do a 4 grouping, you get 2 variable, right? So yeah, if you could do a 4 grouping, you wanna do it, you get less variable. Yeah. So 5, 7, 13, 15, what is this grouping gonna give us? What term? Yeah, BD, right? Because they're both, or all the 4 are in the B row and also the D column. So this will be BD. All right, we're not done. We gotta count for 9 and 11. So what would you do there? Yeah, exactly. Yeah, 4 grouping like this. Okay, and what term is that gonna give us? These 2. 80, yeah. Okay. Everybody good? All right, let's do this one. Again, grouping ones. Yeah, I was hoping somebody would say that first because there's something interesting about the other ones that we'll get to, but yeah. This one should stand out because actually we did it above there too, right? Which term did this give us? BD, okay. But here's the reason I gave this particular example, because of these ones that are in the corner. Good question? Right, you can, and it goes back to what we talked about earlier. that these edges and these edges, they all touch. So it's like a sphere. So these corners are like the pole, the earth, if you will. So corners are a 4 grouping. Right, so usually how it's shown is like this. See, that's the 4 grouping. So what's common to the corners? What variables? Not B, yeah, and what else? Yeah, not B, not D. See, the corners are in the not B row and the not D column. So this would be or not B, not D. All right, you ready for the last one? All right, here, let's group zeros. Okay, so here we want nada by grouping 0. Then we have some don't cares. So what would you do in this case? First of all, what would you do with the don't cares? Yeah, would you make them 1s? Yeah, I agree with that. Make these 1s. Right, because if we made any of those don't care 0s, we'd just add variables or add terms. Okay, so how are you gonna group the zeros? Say that again?
0, 4, 12.
Yeah, this column, yeah. That would be a 4 grouping. So what term would that give us? Yeah, not C, not D, very good. All right, and then what are we gonna do with this 0? Yeah, you just group it with the 8. And that's gonna give us a 3 variable term, and what is it gonna be? A, not D, no, there's another variable, right, because of the 3 variable. Yeah, so it'd be A, not B, not D. This C changes, right, because this 0 is in the not C column, and this 0 is in the C column, so that's why you don't see C. Okay? One thing I probably shouldn't have mentioned right at the beginning is, the reason why you would want a reduced expression in the first place. Like, what's the advantage you think of having less terms and less variables?
Simple.
Makes it easy, yes. Why is it easy? Yeah, and why? I mean, you're right, but why? Exactly, exactly, and it's because, remember, when you have an SOP equation like this, what kind of gate is that? To get this term AB, what kind of gate do I need? An AND gate. And then those AND gates are OR together, and each OR, like each term you have, is an input to that OR gate. So if I have less terms, that's less AND gates, and it's less inputs to the OR gate. So it's a smaller logic circuit. Right? Instead of having a logic circuit this big, you can have a logic circuit that big that does the same thing. Right? It's more efficient, more cost effective. All those things. Okay, so there's an activity that I'll come around and there's an activity that I'll pass out in a short time here, but before I do, I also want to talk about lab 1. Now, lab 0 is due tomorrow, right? Is that right? Remember, in lab 0, that's the one where you basically go through the video that I have, and you just want to make sure that it sims correctly and that you can download to the board and you can demo that it works on the board. And then remember, there's those 4 items that you turn in, a link to a video that shows that your design works on the board. And what shows that the design works on your board is that you flip the switches to correspond with the truth table, and the LED should be on when there's a 1 for that input combination and should be off when there's a 0 for that input combination. And then also remember, with the simulation should have the same test cases as what you're doing on the board, the ones that were provided. And in your simulation, all the waveforms should be green and the data should agree with the truth table. Right, so you gotta check each input combination and make sure your output is the value in the truth table. Okay, I just mentioned that again because sometimes, especially at the very beginning of a course, this course, somebody will look at their timing diagram and they see that the waveforms are all green. And if your waveforms are all green, that's a good thing, but that doesn't necessarily mean that it's working because you also got to check what the values are for those green waveforms. You could have a green waveform that has an incorrect value. Okay. Yeah, so that's your first lab. Now, lab 1, the second lab, that's due a week from tomorrow, right? So that's due Friday of next week. And I just want to introduce it to you. You won't be able to do the whole thing yet because there's something else that I need to talk about on Tuesday before you can do the whole lab. But if you're done with lab 0, you could start lab 1 today if you wanted to after the activity. So let me just tell you what lab 1 is all about, and then I'll pass out the activity. And once you're done with the activity, if you don't want to stick around for the lab part, you don't have to. But you're always welcome to stay. Kathy's going to be here, the ISA for the course. She's going to be here at 2 o'clock. So she'll be here, and of course I'll be here to assist you if you need assistance with either of the labs. Did I turn off the projector? I guess I did. Let me turn this back on. Wow. I saw you turn it back on. Evidently, we'll take just a minute for the bulb to warm up here. So again, a couple of people came in a little bit late, so let me just repeat this, that what I'm doing, if there's a strike, if there actually happens, the strike actually occurs next week, is like I said, I'll be here, and then depending on how many of you show up, will determine whether I lecture or not. If it's half the class or more, I'll go ahead and lecture. If it's less than half, then I'm just going to have an open lab. Again, you're not required to be here. You're not going to be penalized if you're absent that day. I'll just assume you're supporting the strike if you're not here. Okay, or Cancun, but you could also be supporting the strike in Cancun, right? Okay, so this is your lab 1 assignment. You have this lockbox and it has 4 inputs. Okay, so since it has 4 inputs, how big is your truth table going to be? How many rows if you have 4 inputs? Right, 16. You're going to have a 16-row truth table. And you're told that the box opens, and when it opens, there's an output of 1 for these inputs. So there's like 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 of the 16 possible combinations of inputs will yield the box to open, which is an output of 1. If the box doesn't open, it's equal to 0. So as you can see, the first thing you want to do is draw the truth table, right? So write out the truth table based on this information, and then determine the SOP and POS equations. So these would be the non-reduced SOP and POS. So these are coming straight from the truth table. When you write an expression, whether it's SOP or POS, right from the truth table, generally speaking, that's non-reduced. Okay, so first you do the non-reduced. Okay, then you're going to draw a black box diagram. We can do that right here. We haven't talked too much about black box diagrams. But what we did say about black box diagrams, and it's really all there is to say about black box diagrams, is that they show you the inputs and outputs of your design. So you're going to have 4 inputs. A, B, C, D. And you're going to start with 2 outputs, right? Because you'll have an output that's SOP for F, and you'll have an output that's POS for F. Okay, so what's different in this design compared to lab 0 is that in lab 0, you had 3 inputs, here you got 4 inputs, right? Lab 0, you had an 8-row truth table since there was 3 inputs. Here you got a 16-row truth table because you have 4 inputs. And then in lab 0, you only had 1 output, right? So you only had to write 1 equation in your system Verilog code. Here you're going to have 2 outputs, so you're going to have to write 2 equations. You're going to have 2 assigned equations. Assigned for POS, assigned for SOP. Okay? So that's gonna be your black box, you can call it lab one, or you can call it locked box. Whatever name you wanna call it. Okay? Okay, then we want you to write out the K-map and come up with reduced SOP and reduced PO. So to get reduced SOP, you're gonna circle the ones. To get reduced POS, you're gonna circle the zeros, which is gonna give you SOP for nada. And then when you do De Morgan twice, you're gonna get POS for F. Okay? So this lab, you're basically practicing everything that we talked about, up to this point, essentially. Okay, and then you're gonna, in Vivado, you're gonna build the circuits by inputting those reduced expressions. So, notice you're putting the reduced expressions into Vivado, not the non-reduced. So this is the first part of lab one. Like I said, you won't be able to finish lab one based on today's information, but you can do, basically half of it. See, the second half of lab one, we just scroll down a little bit. The second half of lab one is you're gonna come up with a reduced NOR, which we haven't talked about. We're gonna talk about that next class. Okay, so after next class, you'll be able to add a third output. So you'll have this third output, NOR. Okay, but you can't do that one until, you can't do that third output until next class, okay? All right, so before I pass out the activity, or as I'm passing out the activity, are there any questions about anything that we've gone over? Now, when you get the activity, yeah, to tell you the truth, I don't know why after the popular letter of variable for logic output, there's probably some reason. But yeah, you can use any variable. Yeah, there's nothing special about that. Now, what's that? There's nothing. Yeah, as far as I know, like I said, every logic book I've ever looked at, they usually use that. There must be a reason, but I don't know what it is, but it doesn't really matter. Now, when we get to what's called sequential circuits, which is, like a month or 5 weeks away, and it's a while away, you'll see there that there's a certain device used in sequential circuits where the output is always Q. So there it matters, but here it doesn't. All right, so when you get the activity, you're gonna see that there's 8 Carnot maps. So for all 8, I want you to come up with the reduced SOP. And in addition, for only the 4 that are to the right, I want you to also come up with the reduced POS. So there's a total of 12, right? You're gonna do 8 reduced SOP where you circle the ones, and then you're gonna do 4 reduced POS where you circle the zeros and do De Morgan twice. Okay, and my answers are up there for you to compare.